All right, so what I want to do is go over isotopes again, because that's going to lead into weighted atomic mass averages. And and this is going to be part of the worksheet as well. So it's important to understand the notations and what it is. Okay, first of all, an isotope is, well, you have to have more than one isotope to compare the two, but an isotope basically is two atoms that differ in the number of neutrons, but not protons. If they differ in protons, then they're a different element. So every time I come this way, I start coughing. I think because of the smoke. So an isotope is, again, protons are the same, neutrons are different. The chemistry is almost identical. It's rarely you see a difference between the two isotopes, chemical-wise. One weighs more than the other one, though. So if there's anything involving a weight modality, you'll see a difference. For example, in a mass spectrophotometer, mass spectrophotometers are sensitive to mass. So a mass spectrophotometer then would be able to detect different isotopes. Also, during them, who's heard of the Manhattan Project? Anyone? A couple of you. Okay. Manhattan Project was initiated by FDR, Roosevelt, during the Second World War to develop an atomic bomb. What they needed, though, for that process to work was something called uranium, but it had to be a special uranium. It had to be uranium-235. Now, if you go to the Southwest and dig up some dirt, you'll probably find uranium-238. 238 will not work. 235 will. Problem is, 235 is very, very rare. So back in Tennessee, what they did is they developed a big centrifuge that will be able to detect the difference between the heavier 238 and the lighter 235. So in that sense, the chemistry is different. Also, 238 is much more stable than 235. That's why there's abundance of it. And 235 is not very stable at all. That's why there's very little of it. In fact, when you bombard 235 with a neutron, it becomes U-236 and splits apart, called fission, and gives off tons and tons and tons of energy. And that's how the first atomic bomb worked. And most power plants, atomic power plants, work on that same principle. Much more controlled, though. Okay, so as a review, the top number is protons plus neutrons. The bottom number is how many protons, or the atomic number. Okay. Now, as you can see over here on the left, elements are not distributed equally around the universe. Some isotopes are much more stable than others. And when we get into talking about the percents, we need to rename this top number. It's called the atomic mass. So the atomic mass, which is the sum of the protons and neutrons for uranium, 235 is 235. Atomic mass for uranium 238 is what? 238. Now, if we took all the uranium in the world and tried to figure out an atomic mass that represents all of the isotopes, you're going to get something called a weighted average. And that's based on the percent of prevalence. For example, if we look at carbon, okay, carbon is mostly carbon 12, a little bit of carbon 13, and very, very little of carbon 14. So on the periodic table, if you look at that, carbon is, the decimal number is 12.01. Okay, now that's an average of the carbon 12s, 13s, and 14s. But because they're not an, excuse me, because it's not an equal average, it's going to be skewed to the one that there is most of. So with carbon 12, oh, excuse me, with carbon, it's 12.01, which by not looking at that percent over here that I just circled, which isotope is there more of based on the decimal number on the periodic table, 12.01? Which 12, because there's more 12s than anything else. So the decimal number then is going to be skewed towards the one where there's most of. Now, if you're going to do a problem, using the percents, what you're going to do is you're going to take the percent of each atomic mass times the percent and add them together. So, for example, this one here, looking at chlorine. So chlorine has got 'So those are the two main isotopes of chlorine. We need to figure out how this number here is derived. Okay, so you look at the atomic mass, which is the top number of each isotope. And multiply by the percent. So looking at that, which is same as this, okay? When you do that, you're going to end up with 35.45 AMU. AMU stands for atomic mass units. Now we're going to be using this in Unit 4 a lot. Now that number can be 35.45 AMUs or grams in a mole. And that's what we're going to be focused on in Unit 4, the grams part. But for right now, it's just atomic mass units. Okay, so, and of course, the other way to write this would be chlorine 35 or chlorine 37. Now, okay, that's chapter 4. Now, I always have a review at the end. So basically, a little bit of the history of the development of the atomic model. Something about the subatomic particles in an atom. And remember, we focus on 3 of them, but there are a whole bunch. I mean, a lot. And they have all these Poissons and Musons and all these funny names, quarks. But these are the 3 main ones: electrons, neutrons, protons. All right. How the periodic table is organized. And we have 4 groups you need to know: the alkali metals, the alkali earth metals, halogens, noble gases. What is an ion? What are the 2 types of ions? And there's a cation and an anion. Cations are positive, anions are negative. How do you form an ion? Either the atom captures an electron or emits an electron. If it emits an electron, there's 1 less negative particle there, so that makes that a cation. If it captures an electron, it becomes more negative, so that then it becomes an anion. The number of electrons emitted or captured determines the charge. If you emit 1, that'll be a positive 1. If you capture 2, it's a negative 2. So you have the number of electrons, then you need to know whether they're coming or going. Isotopes. Remember, isotopes differ in the number of neutrons. Protons are equal. Chemistry is the same, almost. And then how to calculate a weighted average, which is that decimal number. Okay. Now, what I'd like to do is show you that. Are there any questions about chapter 4? Now, if you go to lecture notes for chapter 4, there's some suggested problems as well. Those are not to be collected, and the answers are in the back of the book. This is what that worksheet looks like. And you're gonna have this on your test. Something similar to this. Not as long. I'll probably have 3 neutral atoms and 3 ions. And make sure you do these worksheets. And basically here you're going to be naming. And of course the answers are here. So in the first column here, you're going to be naming it, naming the isotope. Here's going to be the symbol. This is going to be protons. Let's see. You see the column here. So atomic number of protons, and remember, those are always equal, no exceptions, always equal. Okay, and you've got the number of neutrons, number of electrons. Now, notice here that the electrons are different than the protons. Which is more, protons or electrons? Electrons, hence a -1 charge. Okay, so you look at the protons and electrons, those are the charged particles in there. The neutrons, it doesn't matter on the neutrons because they aren't charged. And then over here, this is the atomic mass in AMUs of the particular isotope, not the decimal number on the periodic table. These are integers here, not decimals. A lot of people put on the decimal number, not the decimal number, because all you're doing is you're adding up the protons and neutrons. Okay, one sheet is ions, the other sheet is neutral. Now, if I don't tell you it's an ion, assume it's neutral. Okay. Okay, so is this make sense? Okay, good. Now I want to get back to chapter 3. It got really interrupted last week. Chapter 3 is a little bit more on things like a little bit getting into the chemistry more. Whenever you have a reaction, like this reaction here, you always start with the reactants and you end with products. Now, as we get into it, we're going to be looking a lot at these numbers up in front here. Those are called coefficients, and they have to be set up to conserve mass and conserve the number of atoms. And the way we're going to get those numbers is when you're doing something called balancing equation. And that's how those coefficients are derived. And we're going to spend quite a bit of time on that. But basically, all reactions look like this. This is so reactants are unstable compared to products. That's important, that word compared. So the reactants are unstable compared to the products. If the products are more unstable than the reactants, nothing will happen. Okay, this only happens if you can make a more stable product. Now, this is the statement I just said is 99% correct. There are some exceptions to that, but in general, we go from unstable reactants to stable products. Now, unless we're looking at nuclear chemistry, if we start with 100 grams of reactants and they produce a product, the products, all the products are also going to be 100. If not, we have a big explosion. And the explosion is related to that, where mass and energy are interconverted via speed of light squared. Now, speed of light is really fast. It's 300 million meters a second. So 300 million squared is a big number. So anytime you lose any mass, when it goes to energy, there's a huge amount of energy. So conservation of mass means that we're not going to lose any mass on purpose anyway, except nuclear chemistry. Okay, so conservation of mass. What we start with, we end with. Now it says behavior matter is driven by energy. When I talk about stability, that's what I'm talking about. And the energy is potential energy. Potential energy. Now, potential energy is the energy that can be obtained if something's done in the right way. For example, at this point, this has a certain amount of potential energy. It has less potential energy now. Where did the energy go? It doesn't go away. It's converted to kinetic energy. It doesn't go away. Which is more stable, do you think? The one down there or up here? Up here? Down there, right. That means that has less potential energy. Less. Now, in chemicals, that potential energy is stored in bonds. So when you break a bond, okay, you're releasing some potential energy, and then the bonds are going to be reformed on the product side. And what you end up with products is less potential energy in the bonds. And to go from the reactants to the products, okay, when going from reactants to products, one, mass is conserved. Number two, the potential energy is lowered because it's more stable. Just like this calculator cover, okay? It naturally goes to where it's more stable or there's less potential energy. So in this reaction, the potential energy is lowered. Now, frequently in chemistry books, they don't say potential energy, they just say energy. Because there's a modified form of potential energy called Gibbs free energy. Don't write that down. And it's the same thing, only it's got entropy built into it. But right now, all you guys need to know is that potential energy goes down, it's more stable. That means when the bonds are broken and reformed, those new bonds have less potential energy in them. Okay, so for a reaction to happen, okay, so the butane looks like this. Got 4 carbons, oxygen looks like this. So those carbon-carbon bonds and carbon-hydrogen bonds are going to be broken. And then they move over here to form new bonds. And the aggregate of reactant bonds that are broken have higher potential energy than the aggregate of the product bonds reformed. So there's a net loss of potential energy. Now, you'll frequently see graphs with just energy on it. And remember, that energy is potential energy until you're told otherwise. When you get into 1A and 1B, they'll talk about it's G, which is Gibbs free energy. But for the most part, potential energy is the culprit there. And there's a fancy word for potential energy. Called enthalpy. So enthalpy and entropy are the 2 driving forces in the universe, okay? But for our class, it's going to be potential energy and enthalpy, okay? The enthalpy needs to go down, energy needs to go down, potential energy needs to go down for a reaction to happen, okay? Now, that's a chemical reaction, not a physical reaction. Melting ice has some energy changes as well, but there's no chemistry going on there. No bonds are being broken. That's the biggest discrimination between chemical reaction, physical reaction. Okay. Okay, whenever we change potential energy, it's got to be transformed into something else. Usually it's kinetic energy. Now, the kinetic energy can manifest itself a lot of different ways. Who could tell me what kinetic energy is? Hmm? Yeah, it's the energy of motion. Exactly. Motion. Now, the motion in chemistry are the movement of molecules. Molecules are constantly moving. And to measure that movement, we have something called temperature. So temperature is the measurement, the metric we use for the measurement of kinetic energy. Okay, so, and the temperature is Fahrenheit or C. Fahrenheit and C are relative temperature scales, and they're based on water freezing and boiling. The problem is it's relative. So to get rid of that relativeness to water, they invented a scale called the Kelvin scale. And that's also measured in the same units as centigrade. So at 0 Kelvin, there's no motion of the atom. That means it has no kinetic energy. And that's really cold. It's minus 273 C or 0 Kelvin. So it differs from Celsius or centigrade by 273 degrees. Energy is constant, and the energy is made up of a lot of different kinds of energy. So when something happens, there's an interchange between, for example, kinetic and potential, but the sum is the same. So when we break a bond and reform it on the product side of a chemical reaction, potential energy is changed into kinetic energy by loss of heat. So you'll feel it get hot. So when you burn butane in your lighter and oxygen, the butane molecules are broken apart, losing their potential energy. The carbon dioxide and water are reformed, regaining some of that potential energy. And in the interim, kinetic energy is given off in the form of heat. Bottom line is potential energy goes down by the same amount that the kinetic energy is given off. It's just an exchange of one for the other. Like in a hydroelectric dam, that water that's high on one side, and what does it do? It falls down through the dam, turns turbines, so it's converting that kinetic energy into work energy, and then it X's out the bottom with less potential energy. So the difference in when the water falls down, that's interconverted to kinetic energy, and the amounts are the same.
Is the
Yeah,
is that measurable or is that
yeah, yeah. It's very measurable, actually. So there's energy is also measured in wavelength. And so if the energy's wavelength is in the visible, we can see it. Usually it's not, unless you're a bee or something like that. But bees can see UV or infrared. I forgot which. They can see one, we can anyway. So again, kinetic and potential together make up the total energy. And you can,
Are they like codependent? So like one goes down.
yeah, they're very codependent. Yeah. Okay, so the unit of energy is a joule or calorie. Those are the ones you've probably seen mostly. Calories for your diet, for your food, you always see calories. Joules, notice they say SI up here. SI stands for Systemic International. It's an organization in France that puts together the world's standards. So the standard unit of energy is the joule. It's uppercase J. So if you're in Nigeria, United States, or Russia, that unit of energy is still the same, a joule. Calories are an older form. They're not an SI unit. And there's two kinds of calories. There's the kind you eat nutritionally, and there's the kind you measure. The kind you eat nutritionally is 1,000 calories, and it's capital C as opposed to lowercase c. So whenever you're seeing the energy on a food label, those are kilocalories, not plain calories. And they abbreviate it with an uppercase C. Okay. More of an engineering unit of energy is a kilowatt hour. You'll see that all the time on the news when they're talking about the grid. The grid can provide so many kilowatt hours. Usually it's gigawatts, but it's still basically kilowatt hours. And that's what you pay for. Usually it's about 15 cents a kilowatt hour. It's not too much. So your light bulbs, they always say turn off light bulbs. Light bulbs use so little energy. LEDs use almost no energy. What kills your electric bill are things that use resistive heating. That would be your oven, your dryer, your air conditioner. Those three are the biggies. So if you want your bill to be high, use those between 3 and about 8 o'clock at night during that heavy use time. And your payment for kilowatt hour is usually triple because they want to discourage you from using that. So they just make it expensive, especially students and teachers that have very little money. Yeah, is exactly what it is. Yeah. Okay, so here's some conversion factors. Remember, whenever you have an equal sign, that's two conversion units. So we can have always two conversion factors. Okay, let's see here. Okay, so we have a chemical reaction going from reactants to products. Potential energy goes down, and that potential energy is converted into kinetic energy in the form of, now energy, like I was answering his question, energy is a wave. And the distance from the trough to the trough is called wavelength. As the wavelength increases, that energy will manifest itself differently. If the waves are really short, instead of like this, it'll manifest itself as light, visible light. Hence, you'll see it. If it isn't short like that and long, it's manifested in heat, so you'll feel it. Remember, energy is a wave. Okay. If the reaction gives off heat, gives off kinetic energy, it's called exothermic. There's an endothermic reaction and an exothermic reaction. Exothermic reactions get hot, usually, or you can see them with light. Most of the time it gets hot. So whenever a reaction gets hot, you know that that potential energy of the bonds has been converted into kinetic energy. Kinetic energy, the molecules are moving, it's perceived as heat. Notice this graph, it just says energy. It's potential energy. Now, okay, and these are products, reactants, products, reactants. So if the energy goes up on the right there for the endothermic reaction, if it's in your hand, your hand will get cold because it's taking energy, kinetic energy out of your hand and converting it to potential energy. So as energy leaves the reaction, that's exothermic. Exo, thinking of exits. Endo, they're coming into the reaction. Kinetic energy is required for the conversion to potential energy. So it gets cold. So if you have a cold pack and you break it, it gets cold. So that was an example of an endothermic reaction. Heat packs, you break it and it gets hot. So an exothermic reaction. Okay. So this is an example of an endothermic, exothermic reactions. Okay. As I was saying before, temperature is the metric used to measure the kinetic energy or the motion of atoms. Kelvin is going to be, it was developed quite a long time ago, but it's developed to show the when no motion of the atom exists. It's zero motion. That's why it's called an absolute temperature scale as opposed to a relative temperature scale. Heat and temperature are not the same thing. Temperature is a measurement of heat, but it's not heat. It's just the metric we use to determine the amount of motion going on in the atom. As you all know, Fahrenheit, water freezes at 32 degrees, boils at 212. Celsius, 0 and 100. The science community uses both the C and the K scales. Engineers will go back and forth. There's an absolute temperature scale for the Fahrenheit scale as well. It's called R, and that's the absolute temperature. So there's R and K. K is the one we use in chemistry. Engineers use both. I took, when I was in graduate school, I took a bunch of classes in the engineering school, and they do things really differently. They switch back and forth between those temperature scales all the time. It was, in the beginning, it was kind of confusing, but you get used to everything. So, okay. So there are conversion equations to go from one scale to the other. And this is what they look like. So to get the Kelvin, if you know the centigrade or Celsius, you just add 273.15. You automatically get Kelvin. And then if you're given Kelvin, you want to convert to centigrade, then you subtract. So that's the easiest one. The harder one is going from Celsius to Fahrenheit. Then you have to subtract 32 or add 32, and it's a ratio. There's a ratio you have to do. Now, in my class, I don't like to go from Fahrenheit to Celsius or back and forth, because in chemistry, you're never going to use Fahrenheit. Never. The only time we use it is in a conversion problem. So I usually don't mess with Fahrenheit too much because you'll never use it in there. You'll use C all the time. And K, when you get into 1A, you'll use K. Okay, all right, so these are just examples of converting. And now this is something that's real important. It's called heat capacity. And it has to, notice the unit has got joules, grams, and degrees Celsius in it. And basically what heat capacity is something retains heat. For example, if you have a glass of water and a glass of feathers, which retains more heat, the water or the feathers? Water. So water has a higher heat capacity than the feathers. Retains water. In fact, water is really unique because it retains a lot more water than other things similar to it. Now, basically, when they talk about heat capacity, they're talking about how much heat is required to elevate a certain amount of water a certain number of degrees. There's three parts to that. You've got to have the heat capacity of a particular item, and they're all different. They have to be given to you. You have to know the difference in the temperature change. And you also have to know the mass of what you're changing. Okay. So this is mass. The delta T is the change in temperature. And then we have the specific heat capacity for that object that's being heated or cooled. And as you can see here, it varies a lot. We have, you'd think iron would have a lot of heat capacity. It doesn't keep it for very long, where water has a lot. And there's a way to change that heat capacity also. For example, in cars, our combustion engines create a lot of heat when it burns the gasoline, the carbon dioxide and water. And so the engine is designed to take that heat away from the engine so that it doesn't melt. And that's done with the fluid in your radiator. Used to be a long time ago, it was water. Now it's a mixture of water plus antifreeze. And the antifreeze makes the heat capacity of the water higher. So it's able to carry more heat out of the engine. That's the purpose of antifreeze. Also, it keeps the water from freezing also. So it does two things. Keeps it from freezing and also increases the heat capacity of that solution. And in 1A, you do all these calculations and stuff. But basically, heat capacity is up there for pure substances, not a mixture. Okay. So whenever there are four variables. And you have to be given three to solve any heat capacity problem. You have to be given the change in temperature, the specific heat constant for the object you're heating or cooling, and then how big is it? How many grams is it? Then there's the actual energy itself. Those are four, you got to be given three. Okay. So whenever you're given a heat capacity problem, look for at least, your three variables in that equation. Remember, there are four variables again. You're going to look for three of them. Sometimes they'll give you the energy. I'll say, I have 10 joules, 5 grams of water. How much can I heat it? So remember, there are four variables, not three. They talk about three here. It's really four. Okay. It's a real simple equation, but there are four. For example, in this one, we get delta T. Q. Mass. So what they want you to do there is to find C, the fourth variable. It's always four. So this is a standard dimensional analysis problem. Okay, these are just more examples here. Huh? What do you want me to do?
I'm just saying that's the solution.
Oh, yeah, I'm sorry. Yeah, because you're going to be solving for C. So you've got equal to, right? Solve for C. And then just plug it in. That's you're asking, right? Now, in this problem, they're asking you to determine whether this rock is pure gold. So what we're doing is we're matching C, the heat capacity of gold, to what it should be. If it's not C, then it's not pure gold. Could look like gold. The other thing in lab, we were talking about density. Density is another property that's specific for certain things. Fool's gold and gold don't have the same density. They also don't have the same heat capacity. So there's two ways you can test whether your sample is really gold or not. Most gold, jewelry gold, is mixed with copper to give it some strength because gold is pretty soft. So they mix it with copper and it's much stronger. That's where they get the carats, like 10 carats, 15 carat, 5 carat, 0 carat. That's called fool's gold, 0 carats. Okay, so that's the main part I wanted to cover in chapter 3, was the heat capacity related problems and this concept of energy. We need Dramamine in a while here. This here. Okay, so make sure you understand this concept going from potential energy to kinetic energy, hot, cold, endothermic, exothermic reactions, and then also the heat capacity problems. Okay, so that is unit 2. And our test on unit 2 will be next week. And you will not have a take-home problem. It'll be just an in-class test.
So what makes like specific heat related questions on the test for us? Like with the specific heat, like what we just went over for that. Cool.
Look up chapter 3 review or lecture notes, chapter 4 lecture notes, and there's some problems in it I assign based on your chapter 3 and chapter 4 in your book. And I assign odd numbers so you can get the answers. Okay, now forgot to test this Tuesday or Thursday. You remember have their yeah, let me switch over to Canvas. Oh, that's okay. I can find it here. So we can either have the test on Tuesday or Thursday. I'm going to start chapter 9 on the other day. So how's this for being democratic? Tuesday, hands, raise your hands for the test. Looks like it's Thursday. Okay, so what I'd like you to do is study hard this weekend and come to me on Tuesday with some questions. You want details? We'll have some time to go over that. Also in lab, if you want to bring up some questions in lab also. Yeah. 3 and 4. Yeah. Yes. Huh? Okay, why don't you ask for a refund and I'll just, it's totally unfair that you've already paid your money, right? You already paid your money, right? Has anyone in here got their digital book to work? You know, if you shared that with them, um, what did you bought it, right? Brought the PDF or did you find it? Okay. You might want to talk to him after class. Um, so if he's willing to share it, I won't upload it.
Okay, cool.
Okay, so yeah. It's practice, and it gave you all the answers. And make sure you look at those worksheets too, those 2 worksheets. One's neutral, one's ionic, because some of those problems will be on the test, guaranteed. Okay. All it is just practicing looking at protons, neutrons, and electrons. And on Tuesday, if you'd like to bring those sheets in during after class, we can go over them as well, if you'd like. Practice, because they give you all the answers. Yeah. Yeah. Yes, I will give you a periodic table. Okay. I'm going to also give you a few formulas, like the heat capacity formula, just some formulas. Thing is, if you do enough problems, you'll automatically memorize it. That's the thing.
Yeah.
No, those are just totally separate. But you've got to pass the lab to pass the class, though, because it's a lab class, quote unquote. Okay, well, I'll see you Thursday, folks, in lab.
Is it, are pants necessary for labs?
You have a lab.
Yeah, keep this for just this. Just coming in the.
I was here on Tuesday. Do you have to be simple products?
No, keep that for test 4. Unit 4 is a lot like unit 1 only. It's detailed. That's why in test 4 is gonna be the same. I'm gonna make that your test 1 score as well.
Yeah. So, go back to one of the videos.